Okay. BK, come here, please. Andy, let's see. Guys, now today we are, how many lectures we have had so far for the microscopy? We have had 3. That's going to be the third one. Yesterday they started with Deshaun with 2 photon, I should say, excitation microscopy. Then we just moved to Jack. Jack started about light microscopy. He's going to join us again today when BK is going to talk about electron microscopy to share his results with BK to compare and contrast the resolution in cancer, I should say, diagnosis with these 2 techniques. And now this champion, Andy, is going to talk about one of the most exciting ones in microscopy, which is going to be X-ray microscopy. I was very interested with that topic, but I didn't get the chance to explore that more. And now here's a great chance with the Andy to teach us what is X-ray microscopy, especially in cancer diagnosis or neuroscience. Then, thanks. Let me put that for the presentation mode. Yeah, there is much better.
Hello everyone. Today I will talk about X-ray microscope.
A little louder, please.
Okay. I will talk about X-ray microscope and I will introduce some details. First, I will talk about the history. After the German physics, he discovered X-ray in 1895. Scientists quickly used an X-ray point source to illuminate an object and compute a shadow image of the object of the resolution of a few mirrors. And also after and in 1950s, the Newberry produced a shadow X-ray the microscope, placing the spinner between the source and the target the plant, which becomes the base for the first X-ray microscope. Is to use the last person the X-ray microscope to do some proof.
What do you call that shadow X-ray microscopy?
Because it because the technology for that century they found the microscope is to use like the image they show on the board to see what the shadow look like or something look like. For use the shadow look.
That's right.
Yeah.
Okay, thanks. Next slide?
Yeah, next slide.
Sure.
First, I will talk what is X-ray. X-ray is a form of high energy electromagnetic radiation.
Yeah.
Also, X-ray has a wavelength range from 0.03 to 3 nanometers, from 3 to the 10 power 16 Hz to 3 to the 10 of power 90 Hz. And energy in the range is 108 to 2000 K. And what is electromagnetic radiation? It refers to wave of the electromagnetic field, reflecting through space, carry electromagnetic radiation energy. It's full of energy. It's a high level energy, and it includes waves, microwaves, infrared light, and
ultraviolet
X-ray and gamma rays. It has 3 different parts.
You mean that, for example, by the gamma rays is different from the X-rays, huh?
Yeah.
Yeah?
Yeah.
Gamma,
X-ray, and
which one has the highest energy compared to the X-ray and the gamma rays?
the gamma ray.
Gamma ray. Why?
What?
Yeah.
I don't know.
Who can answer that, guys? Who can answer why the energy of the gamma rays is stronger than the energy of the X-rays?
It has a stronger electromagnetic radiation.
Or it has a higher frequency, because if you remember, we said that the energy is the Planck constant times the frequency of the radiation.
Super.
And because H is a constant thing, PK, then the higher the frequency, Sean and Jack, is going to be the higher the energy. Because the gamma rays has a higher frequency, they have the higher energy. Do you have the gamma ray microscopy? No. But guys, why we do not have gamma ray? At the end of the lecture, I just want to ask you all, if we have an X-ray microscopy, why do we not have the gamma ray microscopy? As long as you have the higher energy, maybe you can probe much depth into the tissue there. I'm going to ask at the end.
It's going to kill the cell.
That's right, because the energy is too high.
And now I will talk the X-ray microscope. And it's the image for how it can see the color is red and yellow. And instruments that use X-rays to produce a large image and small object. To look the detail for cell or board. And the base straps use the emission of X-ray from a pencil to catch an enlarged image on the posterior screen. And it uses electromagnetic radiation in a soft X-ray. Because if the X-ray the energy is too high, it will kill itself.
That's right. That's so true.
And actually the optics is a burst of optics that the X-ray represents visible light, and this is the picture for visible light. That's all the lights we can see from red
Spectrum. That's right.
from red to purple. Yeah.
But can you have the same phenomenon with the X-ray? For example, if you shine the X-ray to a prism like that, because you're talking about the X-ray optics, and X-rays are, let's say, for example, like the visible lights, or Jack, please put the cell phone aside. For example, the X-ray also, like the visible lights, are the radiations with the, I should say, with the frequency. If you have the X-rays going to a prism, what do you expect to happen out on the other side of that prism? Because that's the visible light. It diffracts to the frequency, spectrum of the frequency, which I should say that's the range of the visible light. And then if the X-ray goes there, what happens on the other side?
Because the microscope has lots of mirror to reflect the light, and the light will reflect the small object like here, and there is one bigger and bigger.
But we are going to talk about that later, guys. But I'm going to ask you guys, what's going to happen if you just throw, Andy answered that, and also ask you that question. If you just shine the X-ray through the prism, what do you expect to happen on the other side of the prism?
It's same as spectrum.
When you see that the X-ray becomes color spectrum there?
No, just one line. But
only one ray, because the X-ray doesn't have the spectrum of different, for example, the frequency to be, I should say, diffracted. Then you expect to have the X-ray, but the angles of the diffraction is going to be very different. Super, thank you. Thanks a lot. Here, please continue. Next slide?
Yeah, next slide.
Sure. Andy, you're doing a great job. How did that?
Resolution.
Wow.
The resolution of X-ray microscope is between like optical microscope and electron microscope. And in general, it's 13 nanometer resolution can be achieved using the fractional zoom Planck laser. It's kind of product.
Uh-huh.
Because the X-ray for the reference.
What do you mean by the natural state?
Orange.
Lenses is one benefit for X-ray microscope.
Huh?
First, advantage because it can view biological sample in the natural state.
Natural state. You mean that you can just, for example, use, for example, X-ray microscopy. One, for example, you have a light cell. That's right. You do not have to, for example, you can just view in time what happens inside the cell, huh?
Yeah.
Is it true?
Yeah.
And you said that the resolution is between the optical microscopy, which Jack, please put that aside, between the optical microscopy, which Jack did, and also the electron microscopy, which BK is going to talk about that then, guys. Please, when you're going to talk about your work today, also compare your result with, I should say, with Andy's results to see that, for example, which one has a higher resolution? Which one? Optical or electron microscopy?
Electron.
Electron.
Yeah.
And it starts with the electron microscopy, X-ray microscopy, then the light microscopy? That's what you mean?
Yeah.
Uh-huh. And how was your microscopy resolution? 50.
50 to
The lowest range, 50.
50 to 200.
And now this is 30 nanometers then.
Yeah.
Does it mean that, for example, with the X-ray microscopy can have a higher resolution compared to photon
yeah.
spectroscopy?
Yeah.
Huh?
Yeah.
Are you sure of that, guys?
Yeah, sure.
Yeah.
Good, fantastic. But the highest, as I understand from your slide, the highest resolution is going to come with the BK's presentation, huh?
0.00 nanometer.
Oh, you checked it before, huh?
No. That's
Huh? BK, look at that. I'm going to come for a presentation today, talk about, I should say, resolution and comparisons with the X-ray microscopy and also light microscopy and two-photon spectroscopy. But it seems that you are going to have the highest resolution, as it seems that the highest resolution of the X-ray microscopy is going to be 30 nanometer resolution by the Fresnel zone plate lenses. But what is that? This is 0.7 millimeter.
Yeah.
What is that? This is
For a plant cell.
a plant cell.
Yeah.
Oh, interesting. The resolution is far beyond the maximum. It's 0.7
一个
millimeter.
cell 有
It's 30
有7毫米这
nanometers.
么大，不可能吧？
纳米啊，这是纳米，
不是毫米吗？
这是纳米，millimeter，一乘10的负60毫的。
哦，那不是毫米是啥？不也？
但是这是 nm 嘛，
这不两码？
nm 不是
那 mm 不是不就是毫米是吧？ 0.7毫米是不是？
那这是毫米啊。
对呀。
Guys, remember for tomorrow,
你数学白学
asked
了。
about the resolution, BK.
0.7应该是整个这个图片的。
不是微米。
Okay. Oh, movie, huh?
Yeah.
Oh, movie time. That's great.
我也搞了一个，我那个9分钟的兄弟们。
World's leading analytical X-ray instruments company has developed the Nano 3DX, a high-resolution 3D X-ray microscope delivering submicron computed tomography for both materials and life
每
sciences.
次打开字幕也看不懂，
3DX
听
is
懂就
able
听
to
懂。
image a wide field of view while retaining high 2D and 3D spatial resolution, and it delivers improved density contrast compared to conventional X-ray microscopes. Rigaku Nano 3DX assists in the elucidation and quantification of microstructures, including biomaterials. Pharmaceuticals, cracks, density, coating layer thickness, and foreign particles are easily observed. Nano 3DX is also ideal for imaging high polymer materials, composites, and light metals. Rigaku Nano 3DX is equipped with a fully featured graphical user interface to facilitate activities ranging from research and development to quality control. Nano 3DX is different from traditional X-ray CT microscopes in that the magnification takes place in the detector using optical microscope elements. The Nano 3DX design is a vast improvement over traditional geometric magnification that requires a very small source subject to thermal drift that causes image smearing. The new Rigaku design places the sample close to a high-resolution detector, allowing for a quasi-parallel beam experiment. This means greater instrument stability and shorter data collection times, providing the highest resolution of any X-ray microscope in its class. 3 primary anode materials are available for use in the Nano 3DX, with each anode delivering a different X-ray energy level. The choice of chromium, copper, or molybdenum allows the penetration and contrast to be optimized for any sample size. As the energy of the X-ray radiation rises, penetration increases, but contrast for low atomic weight materials goes down.
What is that?
For pharmaceutical preparations, copper or
Pharmaceutical, the companies which make drugs, like that, for example.
chromium is usually preferred. For plastics, polymers and hydrocarbon-based products, copper or chromium radiation is likewise preferred. Samples containing aluminium diamond metal matrix composites or silicates require high-energy molybdenum radiation. Flexibility in the choice of X-ray energy used is essential to rapid, high-quality, high-contrast imaging. Rigaku Nano 3DX can observe a wide area without loss of resolution. A detector with a large number of pixels, combined with quasi-parallel beam geometry, delivers composite images that cover an area larger than the field of view. High-density resolution allows for high-contrast imaging of light element materials in composites and the detection of air spaces and microcracks in drug preparations. This impressive level of performance is enabled by selectable X-ray energies and a unique high-brightness X-ray generator and optical system. Nano 3DX is capable of 2D and 3D observation of the interior of samples down to the sub-micron level. Equipped with a newly developed high-resolution X-ray detector with stabilized optics to prevent blurring, Nano 3DX achieves a minimum voxel size of just 0.27 microns. Nano 3DX is able to observe a wide field of view while retaining high 2D, 3D spatial resolution. It provides improved density resolution compared to conventional X-ray microscopes. The Rigaku Nano 3DX assists in the elucidation and quantitative measurement of microstructures, including biomaterials, high polymer materials, composite materials, and light metals. Rigaku, leading with innovation. Contact Rigaku today for more information.
Yeah, that's all.
Okay, thank you very much. Fantastic. Thanks, guys, and thanks, Andy. Thanks a lot. It was a wonderful, I should say, presentation. Guys, when we just go back to the class towards the afternoon, you're just going to have, I should say, the lectures from the BK. He's going to talk about, I should say, the electron microscopy. As far as I understood, is that electron microscopy provides the highest resolution in terms of, I should say, the microscopy of the biological tissues and the organelles. Then BK, it's going to be the last one is going to be you. Compare your results with, I should say, with the Andy, with the X-ray microscopy, with 2-photon microscopy of the Sean, and also light microscopy of the Jack. Jack is going to just join you tonight when you have a presentation that he's going to talk about, I should say, his resolution with your resolution. Is it okay, BK?
Okay.
Fantastic, fantastic. Guys, then thank you, and
Yeah.
see you later then.
See you later.